All right, so this second video might be a little bit trickier, slightly more advanced, I guess, concept here, partial sums of geometric sequences. And maybe not the concept is that advanced because it's the same thing as what we were looking at with the arithmetic. Um, but as far as how we get there, we'll kind of walk through that and see how we get that formula. So if we have a geometric sequence here and we want to find the nth partial sum, in other words, we want to add up the first n terms and see what that sum is going to be. It would look like this. So you recall the summation notation. This symbol means that we're adding, and the k equals 1, that tells us what term we're going to start with, and then the nth term is the one we're going to end up with. And we're following just the geometric formula here. So the first term is a, the second term is ar, third term is ar squared, so on until we get to the nth term, which would be ar to the n minus 1. So let's find a formula, and we'll kind of derive this formula here. It's nothing too complex. I think you'll understand this. So we're going to start with the sum of the first n terms that we're looking at. And then we're going to multiply this equation. So we're going to multiply this equation by r. So we get rsn equals, and then we're going to multiply the a by r. We get ar. Multiply the ar times r, we get r squared. Ar squared times r, we get ar cubed. And so if we multiply this one by r, we get this side of the equation. So ar plus ar squared plus ar cubed plus ar to the fourth all the way up to ar to the n. And so to make this kind of easier to look at, we've lined up the terms that are common terms here, or like terms. And so the reason we do that is because we're going to subtract these two equations. So if we take the first equation, we subtract the second equation, we have s sub n minus r times s sub n. So just that term minus that term. And then we have a, so a doesn't have a like term to subtract from. And then all of these are going to cancel out. So ar cancels out, ar squared cancels out, and so on. All of these cancel out. And then we're just left with this one. So we have nothing here minus ar to the n. And so now let's see what we can do with this. We can factor out the s sub n, and we're left with 1 minus r. We can factor out the a, and we're left with 1 minus r to the n. And then we can divide both sides by 1 minus r, and that gives us a formula for the summation of the first n terms in the geometric sequence is a times 1 minus r to the n over 1 minus r. Okay. So you don't need to know necessarily how to derive this, but that is where this formula comes from. But you do need to know the formula if you don't know how to derive it. But I like to think, and I'm pretty sure I'm right on this, if you know how to figure out a formula, that's better than memorizing the formula. Because a lot of times, yeah, there are little pieces in the formula that maybe you have a hard time remembering, especially if you don't use it for a few days or a couple of weeks. You get to the final exam, and maybe you have, is this one n? Is it n minus 1? Is this one, is it reversed? Like, so there are different moving parts that can make it hard to remember exactly what the formula is. But if you know how to derive the formula, then you can always get the formula. And this is not a hard derivation. If you just remember this first little trick, multiplying by r, and then you can subtract it, and then the rest is fairly easy from there. Okay, so let's look at an example here. Well, here we have this kind of summarized. So the geometric sequence, the nth partial sum is given by the formula. So there's a formula again. So find the following partial sum. All right, so now, how many terms do we have? We actually don't know how many terms we have. We have to figure that out. But we do know that we're multiplying by 4, and we start with 1, so we don't really have to adjust this. If we started with like 5 and we were multiplying by 4, and we ended up with something out here, we could do the same thing that we're going to do, but we would need to divide this one by 5, the original. So we want to start with the 1 plus the 4 plus the 16 or whatever it is. You want that first term to be 1 if you're going to do what we're about to do. So in order to find how many terms are in this sequence, we know it's going to be 4 to the n minus 1. So that term is 4 to the n minus 1. So that one is 4 to the 1 minus 1, 4 to the 2 minus 1, 4 to the 3 minus 1, and so on. So 4 to the n minus 1 equals 4,096. Now we actually know how to solve this. Actually, we'll write this over to the left because we still got to find the sum after we do this. But we need to know how many terms are in the sequence first. So let's solve this equation. We know how to do this. We learned exponential functions not too long ago. So let's take the log base 4 of both sides. Now you could, it's not, and it wouldn't take that long to do it, but you could say 4, kind of make a guess, like 4 to the 9th is there 4 to the 10th, and then see 4 to the what gives you 4,096. But this is the foolproof way to do this. So put this in the calculator. We get log of 4,096 divided by log of 4, and we get 6. And so that means that n equals 7. So there's 7 terms here. And so now we need to find S sub 7 equals A. A is just 1, so we won't even write that. 1 minus R is 4. So you have 1 minus 4 to the 7th over 1 minus 4. And we get 1 minus 4 to the 7th, and then divide that by -3. And we get 5,461 for that sum. Okay. And it seems like it should be higher, but you got to think these first few terms are not very much. The next one will be 64, then 256. Those are not adding much. The 4,000 is a lot. The one before that would be 1,024. So the first few terms aren't adding much to this sum. Other thing to well, we'll talk about that in a minute. So let's look at this one. This will be the same thing, but we already know how many terms are going to be in this. So we start at k equals 1. We're going to go to k equals 6. And let's just add these up. So the a is 7. The r is -2/3. And we're going to go to 6 terms. So S sub 6. A is 7. And then we have 1 minus, you could write plus 1 minus -2/3 or 1 plus 2/3 to the n is 6 over 1 minus -2/3. And so that gives us 7. And let's say 1 minus 2/3 to the 6th. 665 over 729 over, and then 1 plus 2/3. I could probably do that in my head, but don't want to make a simple mistake here. And then we'll just put this all in the calculator. So 665 divided by 729, and then divided by 5/3, and then times 7, and convert it back to a fraction, and we get 931 over 243. And that is our partial sum. So that one might be a little bit easier. It's more calculator intense, but we don't have to figure out how many terms we have like we did up here. All right, so the last part is on infinite series. And so an infinite series is just a geometric series that never ends. So we don't have we're not going to the nth term or the whatever. And so this is the sum from k equals 1 all the way up to infinity with our geometric formula. And you can see the ... and there's nothing, which just means we're just going to go forever. And so if R is less than 1, absolute value of R is less than 1, what that means is these terms are going to get smaller and smaller and smaller as we go along. So if R was 1/2 and A is, we'll just say A is 1, so 1 plus a half plus a fourth plus 1/8 plus 1/16, terms are getting smaller and smaller and smaller. And so it converges, which means that you could find the sum. And so even though there's an infinite number of terms, it would eventually converge to an actual number and to a sum. And the formula for this, and if we go back up to this formula up here on the previous page, essentially what we're doing is we're taking n to infinity. So in this case, with the original formula we were using, n was some finite number, 7 in this case. But if we take n to infinity, and say R is 1/2. So we have 1/2 to, can't really write infinity, but let's just say 10 to the 1/millionth, or however many zeros you want to put, or 1/2 to the millionth, whatever. That gets smaller and smaller and smaller. And so R to the n will go to 0 when R is less than 1. And so when that happens, the 1 minus R to the n is just going to be 1. And so we have A in the numerator, so the infinite sum would be A over 1 minus R. And then if R is greater than 1, the series diverges, which means it goes to infinity. It increases without bound. And you can see that if you have the geometric series where R is 2, obviously this is going to just get bigger and bigger and bigger. You're not going to be add up all the terms and get a number. It's always just going to blow up to infinity. So if we look at these two examples, determine whether it's convergent or divergent. If it is convergent, find the sum. So in this case, the A is 2 and the R is going to be 1/5, which is less than 1. So this one converges. And to get the sum, and notice we don't have the n here because the n goes to infinity. So just the sum would be A over 1 minus R. So 2 divided by 0.4, and we get 5/2. So easy enough, easy enough. If you add up all these, then we already have the 2, and then so all of these forever will never pass 1/2 as far as adding them up. Then this one we have A is 1, but then R is 7/5, which is greater than 1. So this one diverges. So you would not be able to add this up and get a finite number. And so that's all you got to do there. So if the R is greater than 1, it's not going to add up to anything, any number that we could write down. So it's just going to go to infinity. It's going to get larger and larger and larger to infinity. Or if R is negative, then if R is negative and greater than 1, then if this was 1 minus 7/5 plus 7/5 squared minus 7/5 to the third, so on, it would still do that because they're eventually going to get so big. Even if one's plus and one minus, the difference will be so big that it won't matter, and so it'll still go to either positive infinity or negative infinity, whichever the case may be. Okay, so that's 12.3. If you have any questions, feel free to email me.